Hello everyone, welcome to our next conversations about the cosmos. We have a very special guest, Louis from the Harvard University. Welcome. We are going to be discussing two different topics today. Black holes and something that is actually possibly even more inspiring, and that is teaching. So we'll start with the boring subject of black holes. So can you make a black hole in the laboratory?
I wouldn't put it this way. I think the reason why you're asking is the work that I've been doing with one of your colleagues here at the university, Mikhail Zajaček. Yeah, it's to take some very well-known trapping mechanisms in the laboratory in the field of atomic physics, and to ask yourself if that's something that could be reproduced on the astrophysical scale. And it turns out the answer is yes. There's different kinds of traps that are very important in the laboratory that are actually used right now to build quantum computers. Mm-hmm. And we've shown already that if the conditions are right, you can actually have those trapping mechanisms in space, and specifically using black holes.
So just for our viewers, these are not black holes in the lab. These are analogs to real astrophysical black holes that allow us to learn something about those real astrophysical black holes, right?
That's right.
So what can we learn about the black holes in the distant universe using these analogs in the laboratory?
Yeah. Well, when this started really, because again, my background is I'm an atomic physicist by training. So I had to build those traps. I had to study those traps in detail. And I remember a long time ago, maybe 15 years ago, thinking, hey, whenever you have the gravitational potential from these, orbiting bodies and everything, I remember thinking, there's definitely some analogy there. At some point, I'm going to have to check this out, right? And I've only decided to do this in the last 5 years or so. So long story short, when you're in the laboratory and you want to confine individual atoms, which again for a quantum computer is what you need to have quantum bits of information, you need to create some electromagnetic fields to be able to confine them in space. And the shape of those electromagnetic fields are saddle-shaped. So the way it works first, I need to explain in the laboratory settings, why is it that we have those kinds of traps? And we need to trap those single atoms, and where each atom is a quantum bit of memory, if you will, in a quantum computer or quantum simulator. And in order to trap those single atoms, you need to use fields, electromagnetic fields, to push them around so that they're trapped. But it turns out there's a very well-known theorem in introductory electromagnetism that tells you that you cannot have a static field, like an electric field, for example, to trap a charged object. You just can't produce that. So the only way to do this is to bring about what's called dynamical trapping or dynamical stability. So you have this single particle here, and your goal is to trap it, single charged particle like an ion, and you can create electric fields in this direction, which will confine the particle along this direction. But unfortunately, physics tells you that it's going to be anti-confined along this direction here. So what you do, though, is that you change the polarity of the field. You go from confining here, anti-confining here, and you switch it around quickly, where it's anti-confining here, confining here. That's the best that you can do.
So it's like you're squeezing in like this, and very quickly like this, like this, like
Exactly.
this, like this, and it's keeping it into place.
Exactly.
Mm-hmm.
So, and if you do this at the right frequencies, and it all matches with the mass of the particle and so forth, you can achieve what's called dynamic stability, where the particle, if it could talk, it would say, I'm in a three-dimensional confining potential. And it may seem like the trapping is a little bit dirty, like you have this movement around like that. But it turns out that these quantum systems are, in my opinion, probably I think objectively are the cleanest quantum systems that we can produce in the lab, by far. So it's beautiful motion, and I'm giving a presentation today, and I'll give you some examples of that in the presentation. So again, just to recap, to trap those those charged particles here, you need to create those fields, and the fields needs to change in time in such a way as to bring about dynamic stability. So now going back into the astrophysical realm, if you imagine having, say, two black holes that are orbiting each other, now the field that might push particles around is going to be the gravitational field, right? And if you think about the gravitational field of those two objects orbiting each other, that's also a saddle. That is, when a particle is between those two massive objects, it's this unstable portion of the saddle. But if the particle moves along this direction here, it gets pushed back toward the center. Here it gets pushed back toward the center. Same over here. So it is in fact a three-dimensional saddle that is rotating in space. So the question is, when you have a particle, let's go back to the lab. In fact, let's go back to something simple, an actual horse saddle here that you were to rotate. Could I put a particle on that saddle and keep it in place there? Could I achieve dynamic stability? And the answer is yes. Again, if the right conditions are met. So that's why I remember a long time ago, 15 years ago, I remember thinking, I'm going to have to study that later. There's got to be something there. But I knew back then an issue. And the issue is that if the real saddle is too steep or not steep enough, it doesn't matter how fast you rotate the saddle, you will never achieve dynamic stability. You have to have the right conditions. And I remember back then, quick calculations told me, you just, with those black holes, it would be very nice, or binary star system would be very nice if the rotating saddle was such that you could in fact achieve stability for some matter that could be trapped between, the two objects, but you cannot. It turns out the gravitational potential is always too steep. Mm-hmm. So the big question is, how do you undo some of that steepness? And I remember at the time thinking, if the black holes were to acquire a charge, like some stars have charges, that was my initial idea, by the way, with stars, then now you could imagine having a plasma that's between those two black holes, and the plasma, like positively charged particles here, let's say, would feel the gravitational potential, which is too steep. But now if the two black holes have a small positive charge, now this electric potential could undo a little bit of that too steep gravitational potential. And if the charge is just right, then it turns out that the net potential steepness or the net saddle that you end up with is just perfect. And ended up finding out that indeed black holes can have a charge. And we have someone here, Mikhail Zaczek from Masaryk University that wrote some now I think famous papers on that. And that's when I realized, oh my goodness, we can actually do this. And interestingly, in this paper, I remember distinctly where I was sitting in my house, where I saw the approximate charge that these black holes could have. And it's very small. And I remember quickly calculating that this very small charge is exactly what we need, or in the range of what we need to have trapping. So that's when I communicated with Mikhail and asked him, because I'm not an astrophysicist, and asked him, for help on this. And we've been collaborating since. So that was a long answer to a pretty short question.
Would the plasma have some preferred shape, being swirled around by two black holes? Would it be like spherical, like a sphere of plasma, or I don't know, what would be the shape?
That's
or
a good
no
question.
One knows.
That's actually, the undergraduate student, his name is Ali Kurmush, from Turkey, who was one of my students at Harvard University. He's the one who took a research for undergraduate course that we have there. I think he spent a year with me, a year and a half. So he did lots and lots of simulations, and he's the first author on these papers. The shape is most of the time circular, but of course it depends. Do you have the two black holes of the same mass? Maybe there's a mass difference, maybe a charge difference, but no, the shape is mostly spherical. So, not to get too technical here, but if you confine the plasma ball to be a little bit cold, then it's going to settle toward the center of the saddle. And at the center of the saddle is quadratic or hyperbolic. So you do expect something that's round in shape.
And when you heat up the plasma, it would start expanding.
Yes, and get ejected.
And can it have a temperature that can be actually visible? Like we can be observing a pair of binary black holes and something radiating from the center?
Yeah, that's the question, right? Because what I just described is at a minimum a really cool toy system, right? But it turns out the amount of the single component plasma, which is just positive charges that you can trap, is too small for you to see. So that's why that's the first paper that we published, and where I think we're pretty clear in the paper. We say, look, this is the first time, as far as we understand, that anybody presents an idea of non-orbital trapping, right? It's a new idea in astrophysics, right? Typically, if you want to trap matter, it has to be in an orbit around a body. But the idea to just trap matter somewhere in space, that's never been visited before, other than those Lagrange points, which are not stable anyway in all three dimensions. So that was the original part of that paper. But as far as being able to see that plasma, it's too small to see. So that's why in the back of my mind, there was always this next project, which instead of being what I just described, RF radio frequency pole traps, those are very famous. In fact, the people who discovered that won the Nobel Prize in 1989 for that, Wolfgang Paul. There are other traps that are equally famous called penning traps, and they work slightly differently, and I'd be happy to describe those. Now, what's nice about those traps, and that's the paper that we actually submitted to Nature magazine and now under review there, now you can trap a very large amount of matter, and for sure you can see something there. And if you can see something that's trapped between the two black holes, that's what allows you to see what would otherwise be invisible black holes, like stellar mass black holes, right? That don't accrete matter, so you can't see them. But again, if they trap the plasma in between, there are ways that you could see them.
So, do I understand correctly that the small charge that the black holes can acquire can have a big effect on their observability as well? That when you have a binary black hole, where both black holes have a small charge, that that small charge changes their properties, the observed properties, I don't know, at radio wavelength when you are observing, or?
Yeah, but that is only if the plasma that this binary system is trapping would be visible. But it turns out the amount of plasma that it can trap is too small to be seen, unfortunately. But in principle, yes, you could see a bright dot there in space, and you could look at how it's moving, and you could infer
but
that.
I'm asking because you just said before that in certain conditions are met, that actually it can be larger amount. So
That's for a second kind of trap, where in the second kind of trap, you no longer have to rely on the black holes being charged.
okay.
So before moving to the other way of trapping stuff between black holes, I just want to ask, what is the period of the rotation of the two black holes? Because if it is short enough and they are close enough, they should be radiating also gravitational waves, and that can be disruptive in a way. So what's the time scale?
Of course. Well, it depends how far apart they are from each other, but it can be as little as hours when they're very close to merging. But in general, the time scale that we're looking at in general are fiducial sort of configuration. That is, if you look around at black holes, we say they're about one astrophysical unit apart from each other, just roughly, right? And when they're that far apart and they're one solar mass, I don't remember the numbers, but it's it's on the order of a year, right? The
So it
orbital
can be
period.
very slow,
Very slow,
very slow,
correct.
and still trapping something.
Correct. Whereas in the laboratory, it's megahertz.
Yeah.
It means millions of times a second, yeah. But yeah, so what I just described now is one kind of trapping mechanism that's again, it's what produces the cleanest quantum states that I know of, other than maybe light in cavities, like photons when you have those high finesse cavities and quantum optics. But yeah, so this is dynamical trapping achieved by changing the potential in time. And there's a direct analogy using those black holes. And by the way, for those of you who may have thought, hey, why black holes? This would have worked just the same if it was stars.
They are just cooler.
So, in fact, initially, like 10 years or whatever ago, when I was thinking about working on this, I remember thinking it was going to be stars, right? There was no reason for me to go to black holes. But once I started reading about this, then I realized, oh, but stars are very messy, right? They have, solar winds and all that stuff, which will mess up the plasma in between. Whereas black holes are stellar mass black holes. They're extremely quiet.
Or cool.
And there's certainly the cool factor, yeah.
But also cool, like not hot and not radiating stuff. So
Oh, that's what you meant. I see.
It was
Yes.
a tiny joke. So what is the other way of trapping?
Yeah, so, and this is far more exciting because now it leads to something quite real. And that's the one I really wanted to work on, so for a long time. So, okay, another way of trapping is instead of achieving dynamical trapping by changing things in time, what you do instead is you employ two static fields, a magnetic and an electric field. First, a very strong magnetic field, let's say along the z-axis here, and we're in the lab now, Very strong magnetic field that goes toward the ceiling here, and you throw a bunch of charged particles, let's say that they're positive ions. You throw them in the field, and it turns out that the force that charged particles feel in a magnetic field makes them curl around the magnetic field lines, right? So they're just going to undergo what we refer to as cyclotron motion. It's just a curl around the magnetic field lines. So then you have particles that are sort of trapped, at least trapped on this plane here, just by virtue of being immersed in a strong magnetic field. But if you see those particles will just migrate up like this, and you'll lose them up and you'll lose them down. So what you do is you introduce an electric field. And we refer to that as end caps, where you put an electrode here, and say you charge it positively, those two electrodes, like 100 volts. And these positive ions here, of course, they feel repelled toward the center here. They feel repelled toward the center here. So now you get confinement along the vertical direction with those electric fields. And you get confinement along the equatorial plane here with the magnetic field. So that provides a three-dimensional trap. So that's used, again, in the laboratory, also to do quantum computers, quantum simulators. And now the question again, okay, is there something analogous in space? And it turns out...
Before that,
yes.
Doesn't it just radiate away the energy? If you have a charged particle going in circles, it should be radiating and losing the energy, and then...
Sure. Because it's accelerating, it's going to radiate. But if you calculate the rates, it's very small.
Okay.
Yeah. Of course, if you crank up the magnetic field to...
Then it will just... And...
Yeah, of course. That's a good question. But interestingly enough, in the laboratory, that's a good thing if it's radiating energy, because we want them cold. Because if you want to manipulate particles quantum mechanically, you need to remove all the, thermal energy, which is, what should I call it? It's sort of, random motion. Also, if you remove all this, so that once it's completely removed, typically with laser cooling, then now you can do what we refer to as coherent manipulations. You can say, these are the quantum states, and now that I know that it's in the ground state, the lowest energy state, because I've removed all the energy, it's in a known quantum state, then now I can use lasers to promote it to known quantum states. And you can do something that's coherent and produce beautifully crafted quantum states. So yeah, radiating energy is not such a bad thing, but still, that's not how the energy is lost. It's really by forcing it with lasers. Good question. But so the analogy in space is the conditions that you need would be to have a magnetic field out there. Well, first you need to have a plasma, right? So you have those, plasma-rich regions out there in our galaxy. So you have that. And the second thing that you need are magnetic fields, or are, again, I'm not an astrophysicist, so I remember years ago I had to research this. So I, just like when I reached out to Mikhail, I had reached out to people, one person at Princeton and one person at University of Rochester. They're leading the field in those intergalactic magnetic fields. And they reassured me that there are very large swaths of the galaxy that have very coherent magnetic fields, like in a lab. That is, the magnetic field is not negligible, it's a good value. And of course, on the laboratory scale, it's very small. But over there, it's surprisingly strong field, and it's straight, over very large distances. So I was a bit surprised about that when I learned that, but I thought, whoa, this is good. So we may have a penning trap. But now, if you just have the magnetic field, you just have trapping like this, right? But how do you trap the particles like that? You can't just bring in end caps, right, in space. So that's where the black holes come in. If you have the magnetic field pointed in that direction, and you have two black holes that happen to be orbiting like this, then now if you have the plasma that's undergoing cyclotron motion, escaping in that direction, it gets attracted back toward the black hole pair. And same thing over here. So that provides you with the end caps, which are gravitational end caps. So that's why the combination of this magnetic field, which in combination with not the electric field, as in the lab, but the gravitational field, provides you what I like to refer to as a gravito-magnetic trap, which is a astrophysical penning trap. Yeah.
Cool.
But wait, the coolest part about that is, unlike the RF pole trap where the black holes had to have a charge, and of course when the black holes have a charge, let's say it's positive, now you're tied to having a positive plasma, positively charged plasma in between. You can have a neutral plasma. Whereas in the penning trap that I just described, what was exciting, the reason why I was so excited at the time, is that now you can trap a neutral plasma, which means it can have a much larger size. And in fact, if you have, let's say, 250 solar mass black holes orbiting each other, the amount of mass that you can trap in the center can be as large as like a millionth the mass of the sun, like a very large mass, which for sure you can see. Assuming this whole trap works, for sure you can see it. So that's very exciting.
And are there any known binary black holes in a region with well-behaving magnetic fields?
Yeah, in fact, they're most likely to be found in those regions, in those plasma-rich regions, so thankfully. So you have to run the numbers. You have to say, how many black holes do we think that we have in the galaxy?
On average, yeah.
Yeah, what's the portion of the galaxy that has those magnetic fields? And then what's the portion of those black holes that would be in those regions and everything? And it turns out when you run all this here with large error bars, the hope is that there's a few hundred.
Wow.
Binaries right now that have that configuration, which means those binaries are moving in those plasma-rich region, and they should be vacuuming up the plasma.
So does this trapping work only in conditions when these black holes are still sufficiently far from each other? Or will it work in some way until basically they merge? And might it result in some electromagnetic counterpart of black hole mergers?
Yeah.
Because
of course. Of course. Yeah. No, you're exactly right. So these trapping systems, they undergo parametric resonances. And I'm happy to explain what that means. But straight to your question, when the black holes are getting nearer to merger, so that means the saddle is now rotating faster and faster and faster. As far as the plasma is concerned, now it has a driving force, which is from the quickly rotating, gravitational saddle. And it turns out that this frequency of, the rotating saddle is starting to get close to the cyclotron frequency that's fixed by the strength of the magnetic field. and you start approaching what's called a parametric resonance. And once you have a parametric resonance, it's a very abrupt change in the dynamic of the system. So what's interesting is that as the black holes reach a critical inter-black hole distance, the trap empties almost instantly. And that's what we see in the labs as well. It's not a continuous process.
So when does this happen? With respect to the merger of the black holes?
Yeah, maybe in terms of days, maybe it could be a year before the merger. And the time scale over which the trap will empty, again, large error bars, right? But still, it could be on the order of hours, as short as hours, which is a bit surprising, or it could be days. So if you have, like a millionth the size of the sun, that all of a sudden gets released, the trap disappears in a matter of days or hours, then this would be absorbed by the black holes, would be extremely bright.
So you should see a small signal couple of days before gravitational waves coming from the final moments of the merger.
Or let's say like a year or 5 years, yeah.
This is very interesting because as far as we know, black hole mergers do not produce any electromagnetic counterparts, so anything that we could see with telescopes. So what you are studying are potential sources of electromagnetic counterparts, which will not appear at the time of the black hole merger, but for example,
a precursor,
a precursor. But when we see the precursor, we don't know that is a precursor. So basically, what we can do is that if the merger will be localized with some accuracy with the gravitational wave detectors, then we could go to the archives and then we could look at mysterious electromagnetic counterparts that would have the predicted properties for such black hole mergers.
Which, if I may say, the luminosity can be quite high. Like our fiducial system is on the order of 50 solar mass black holes, which is in the ballpark of what we tend to see with the gravitational mergers. And it turns out the luminosity of when the trap gets emptied, that signal is on the order of 1,000 solar luminosity. So it's pretty high. Yeah, so it's unmistakable signal.
Warning signal before the merger.
Yeah. So that's exciting, and then this project just keeps on evolving. So what I found essentially is and this shouldn't be surprising to anyone, but it was surprising to me somehow, that the fields are very siloed, right? Like when you're an astrophysicist, it's very complicated and you don't have time to really learn about other fields, right? What they're doing in atomic physics, for example, and vice versa. In atomic physics, I'm well versed there, but I did not know anything about astrophysics. So now that I've been dabbling in this thing, and I've been learning a lot from my colleague here, Michal Zascharczyk, there seems to be so many other aspects of atomic physics that have not been brought into astrophysics. So I think it's going to be something that I'll keep doing with undergraduate students for years to come.
Maybe it is a good place to pivot to our other part of the discussion, because yes, also we researchers should be learning to learn quickly about other areas so we can find the connections. But instead of starting with learning, I would like to start with teaching. What's your favorite, not subject, but lesson to teach? Like something from mechanics, something from optics. What's your, this one lesson I'm looking forward to because this will be great? Which one is your favorite?
That's a good question, and I don't know if the answer will be interesting or non-interesting, but it's all of them, but for different reasons. I often teach our largest course in the physics department. It's physics for life science majors, like people that have become doctors. And of course, that's different than teaching our own majors, right? It's quite different. I like to teach them for different reasons. Their motivation for physics is obviously not as high. They take the course most of the time because they have to, not because they want to. I really enjoyed that aspect of teaching. Whenever I teach, physics majors, then there's different factors that make it very interesting. The fact that they're so motivated. So I don't have a favorite.
So I would maybe go to your famous result that when students feel that they understood, it doesn't describe the reality. That often students who feel that they didn't understand that much understood more than those students who feel that they understood. This is very, very interesting to me. And can you tell us more about that? And then I would, I will then follow up with another question. But
well, let me ask you: is that something that you could relate to, as a person who is continually learning things, or thinking back of you being a student, or that's something maybe you lost track of over the years? And you as well. Is that something you could relate to, or not really?
I do, and also as a teacher. Like, there are some students that seem to be confident throughout the semester, and then the exam period is very difficult for them, and then the other way around. Some students feel to be like still doubting themselves, and then they nail the exams perfectly, basically. So there is a great mismatch between the at least perceived confidence and the real understanding of the subject. So,
Sure.
And for myself, it's slightly different, because from the moment you learn the first subject well, you realize you don't know basically anything else. You first have the impression, yes, I know everything in the world, after finishing high school. Then you understand 10% of physics, and then you feel terrible about everything else because I have 0% knowledge of biology, history, So I'm mostly in this mood. I don't understand basically anything, and I'm happy then I understand at least something from physics. So I haven't felt super confident since then.
I see. I like to ask that question simply because sometimes we have to be careful to not assign these very interesting concepts of feelings of learning versus actual learning just to the classroom, when in fact we experience that every day in our everyday life. And that's the best way to understand why this is happening to our students, right? And it is a very, very important effect. So it just turns out that our feeling of understanding or feeling of learning is what's called in cognitive psychology, it's a metacognitive cue. So metacognition is basically you're thinking about your own thinking, right? Like you think, how's my thinking doing, right? That's metacognition. And this is a cue that's very powerful. That is when I'm here now in Prague or in Brno or whatever, and someone gives me directions, and I listen to the directions they're giving me, the perceived fluency that I get from their explanation, thinking, oh, that's very fluent and so forth. I perceive that. It'll typically be very well aligned with how well I actually understand it. So that this notion here, this famous result, now famous result, that our students experience the opposite, that when they think they learn a lot, they actually are not learning as much, and vice versa. This is not what we experience every day. 99.9% of the time, this metacognitive cue, which says the following: if something is fluent, it must be productive. It must be that I'm learning. So this is very accurate, 99.9% of the time. Someone gives you directions, you can tell, wait, that makes no sense what the person just said. It's probably because you didn't learn anything. Or that makes sense what the person just said. It's probably because you learned something. It's in perfect agreement. However, when you get into an environment like a classroom where what you're being exposed to is now a lot more complex information, you don't have, first it's unfamiliar, and you don't have feedback. You don't have anything to grab onto if you're following or you're not following. And it just so turns out that whenever students are learning a topic like physics, right, a STEM discipline, if they're novice learning this topic, they should be encountering a lot of confusion, which inherently, when you're confused, there's a discomfort that comes with that. It's inherent, right? It cannot be avoided. And unfortunately, the mental equation that we make is that if there's an inherent discomfort, we associate that with disfluency. So that means the learning experience feels disfluent. And again, in my everyday life, whenever something feels disfluent, that means it's not productive. And that's true almost all of the time. So it's automatic. The student or the learner will feel like, oh, that must not be productive because it's too effortful right now. It doesn't feel quite right. So it's perfectly normal for students to feel that way. In fact, for us as faculty, we think sometimes, that's just with students. But I always like to remind people, hey, do you go to colloquium sometimes where you happen to have one of those colloquium speakers that's just smooth as silk? You know, like we have those super lecturers, right? People that are very charismatic. And you go to that colloquium and you feel like, it's not my field, but I learned a lot. That person was talking about such and such, and it just felt quite right. And then you rethink about it later, you're like, wait, that doesn't make sense. Mm-hmm. So it happens even to us, right? So not just with our students. So that's basically the effect that we measured. So essentially, that's been known in cognitive psychology for decades. For decades. So why is it that it was such a big deal when we showed it? It's because it's the first time that it was demonstrated in a very complex environment. In psychology laboratories, the experiments are very contrived, right? You're going to have English, Swahili word pairs, and the subjects are going to be asked to remember 20 word pairs. Like, it's very contrived, right? But these results of feeling of learning, feeling of knowing versus actual, retention of information in memory research, that's been known for decades. So a cognitive psychologist hearing this result says, of course.
Okay.
But that it was seen so prominently in a complex environment, that was surprising. Yeah, it's a very prominent effect.
So when we do science outreach, when we are talking to the general public, we simplify things. We need to retain the attention of the people. And we who do science outreach are happy when people tell us, yeah, now I feel that I really understood what you talk about. How should we think about that? Then how to do, and when we do outreach, of course, we are not going deep. We try to explain simple concepts. But do you have any advice for us doing outreach? How to actually break this discomfort and
Sure. Yeah, that's a very good question. Like the likes of Neil deGrasse Tyson, right?
Yeah.
That they have an ability to explain and people feel like they're learning a lot. So this is what I would say. I would say that if your goal, which I don't think it should be your goal, is for people to learn something complicated, because when you look under the hood, most things are a little bit complicated, especially what you are discussing with the public. If your goal is for people to really learn this, then there's gonna be some inherent feeling of disfluency, because it's gonna be hard for them to grapple with these new ideas, right? And therefore, they're gonna have a feeling maybe that it's not as productive. And I would say in this particular case, maybe that should not be the top goal. The top goal should be, providing the viewer with a sense of wonder, maintaining their motivation for the topic, their interest, their personal interest. So for that means that you have to water down the explanations, or you have to be less ambitious about what you want them to learn. But there's a limit. If you keep watering down the explanations to the point where you might as well be giving simple directions to go find the Starbucks over here, then you're not providing much value anymore. But trust me that their feeling of learning will be matched with their actual learning. From that point of view, you'd be very happy. But then you have not provided much value. So you have to find, I think, the right balance. You have to go right where they're starting to feel slightly discomfortable and come back a little bit.
Mm.
And there's no way to know that unless you actually know your audience well.
So you spoke of the sense of learning. Can we be able to judge ourselves? Like, am I actually learning something? Am I understanding this new subject? Or is it just like the illusion of knowledge? How to distinguish those two states? Actually understanding something and just feeling that I understand this.
Yeah, very much so. We become more mature learners, and our ability to be metacognitive about our comprehension gets better and better with the years. That's why for us, intuitively, we don't even think about it, but we always question ourselves. There are mental tricks that we've developed over time, again, just intuitively, without really doing it explicitly, where we ask ourselves questions to check, do I really understand that? Do I really understand what he's explaining to me right now? In fact, when colleagues speak to you, you are doing that. You're constantly questioning, you're asking the right questions, and then you realize, I'm not following. But if you weren't asking yourself those questions, which a novice student just doesn't have the skills to do, then you wouldn't know. You wouldn't know if you're confused, if you're learning, you'd be a bit lost.
But this is a little bit taxing, like asking, am I understanding? And I don't want to say most people, but many people just accept everything and they just say, okay, I think I understand this. I don't want to undermine my own understanding by just investigating it and testing it and so on. So they just accept their understanding of the world and are just happy with it. So is there a way to how to, I don't want to say force someone, but to invite them to challenge their own understanding of stuff?
Yeah, address motivation explicitly. Yeah, it's interesting. In science education, motivation is really at the top of the pyramid, at the top of the food chain, right? Everything follows from students' personal interest. Because if the brain is not interested, the brain's not going to be engaged, and it doesn't matter what else you talk about, right? But interestingly, it's very hard to study motivation. So it's at the top of the food chain, but it's something that's sort of assumed, right? So that's why when you say, is there a way to push, the learner? And then the answer is yes. And you have to address their personal interest, their motivation, and there are ways to do that. And it's interesting, I'm writing a paper on this that I think is going to be important. And the paper is distilling all the knowledge that we have from the research that's been done on motivation for students, and trying to basically distill it into, a paper, like a 12-page paper that people like us can actually read and get some clues from the reading on how to increase motivation for students or for your audience. And there are lots of tricks.
Can you tease some of them?
Sure. So there are 3 pillars of motivation that are known from cognitive psychology. One is just is the learner or the listener personally interested? Is there personal interest there? Yeah. And an issue with us in STEM sometimes are their preferences depending on gender, right? If you have male instructors, sometimes that will only have rocket examples, plane examples, and so forth. Sometimes there's a gender that's not as attracted to these examples as, yeah. So that's an example of what to be careful with. So that's personal interest. The other one is self-efficacy. I hate jargon, but that's the word. Self-efficacy just means that the learner has the sense that if they give it a try, they will actually be able to learn the thing, right? Self-efficacy. Mm-hmm. And I think it's self-evident that if you don't feel that you're going to be able to learn it when you try, you get demotivated, right? So addressing that explicitly is very important for motivation. And the third one is a sense of control. So that's why when you have a traditional lecture, the pace at which the information is being delivered, you have no control over that as a listener. So that's very demotivating. So in a conversation, if someone, dominates the conversation, a bit like I'm doing now, it can be very demotivating. Someone's been talking for 15 minutes because you have no control. But as soon as you talk to a close friend, you can slow down the conversation. Yep. You can shift things a little bit. It's, it's a lot more motivating. So those are kind of a three-legged stool. So I would say, when you ask me, are there ways to address motivation? I would say, yeah, you already know a lot of ways. If you just remember those three legs, like how can I increase that person's personal interest, self-efficacy, and sense of control?
What is the motivation to study science?
You mean for people in general?
For people, yeah, for students. What do you feel is their motivation?
That's a good question.
It's a tough question.
Yeah, unfortunately, I think it's has lots of different answers depending on different personas.
Because, for example, if you are going to study, I don't know, law, then you have in mind you want to study something that will earn you a lot of money. But I think in sciences we are often providing not like the comfort of wealth, but that you will see the world differently, and you will actually. You are there to learn something just for the understanding itself, not for the application of the understanding, but for the understanding itself. And this is something that I would like to know, how to motivate those different type of students, because some just have the goal in mind, I will finish the school, get a diploma, and be rich. And the other is just there for the study itself. So how is the motivation? How can we balance two very different groups? Or it's actually not two different groups, but each of them have two different personas in mind. And
yeah, I think you see that a lot in engineering departments, right? Where you will have some students that, at least initially, they won't express a lot of interest in the, in the theoretical aspect of the discipline, right? They'll just get through the classes because they just, in their minds at least, they like the idea of designing things and so forth. So I've taught a lot of these kinds of students, and there's no workaround. If you're going to address someone's motivation, you have to address one of those three things. And for these people, the personal interest is not the inherent beauty in the physics that they're learning through their engineering program. So you can't even try, from that point of view. You have to meet them where they are, which is, for them, like I love airplanes. So for me, when I was younger, I studied aerospace engineering. So for me, you would have had to come to me with ideas about, aeronautical engineering and so forth, applications, how to do airliners or fast jets or so forth. And then you would have gotten me quite motivated.
This is very interesting because I think our role as a when you science communicator and also as a teacher, at least how I see it, is to arise curiosity, the sense of wonder, to increase the motivation of the students, of the general public, to know more about the field. And then they will go and they will search for information. I cannot expect that I teach everything. Also, maybe this is a personal thing. I always found it very hard to learn during lectures. Sitting in a lecture, I often tune out after 10 minutes. Makes the speaker must be very good to keep my attention. Yeah. So it is hard for me. So maybe this also makes me believe that the most important thing is to help motivate the students to actually go and learn more about those interesting, beautiful things that we care about in physics, learn about the world around us.
Yeah, I don't know anyone who teaches physics who doesn't want to do that, right? We all want to do that, and sometimes it's disappointing that some students don't seem to be initially interested in that, but really it's on us to find ways to make that happen. Like for me, when I teach those life science students, those that are going to become doctors, most of them are not really interested in the physics. They just have to take the course. The part of teaching them that I really enjoy is that motivation part.
And when they are motivated, then they go through all that pain that you are describing, that the discomfort of learning when you are confused, and this is something that everybody, I think, experience at their own speed, and that is the best done over a book. For someone it comes very slowly, for someone faster, and with the frontal teaching you cannot do the speed that is good for everyone.
Yeah. Hence those modern teaching techniques where people can go at their own speeds, But yeah, and also what I like to remind instructors is we're not that different from what would you call it here? People that help you at the gym. They're called
fitness trainers.
Fitness trainers, right? One of the job of a fitness trainer is to keep you motivated, right? So sometimes we think, no, this is not my job. The students should be self-motivated. I beg to differ. A lot of our work should be to find ways to express the ideas that we're teaching them in a way that increases their personal interest, their sense of wonder.
So necessary learning something is an emotional roller coaster. When you have the downs, when you are struggling a little bit, and then hopefully some ups when it's feeling like you learn something and it clicks. And it's a nice feeling when it clicks.
Yeah.
And you have the eureka moment when you finally at least feel you understand something. I think this is also like the role of the teachers, provide this feeling now and then, like something you kept hearing about and then finally you at least feel you're understanding. I remember this point when first I saw the Maxwell equations derived. I kept hearing about them before then, and then suddenly someone explained it. I was like, oh, this is great. So this is also probably part of the motivation, giving those feelings. Finally something clicked.
Thank you very much for this very nice conversation. I think it is it's a great perspective and
very motivating.
Yeah, very motivating.
Hopefully it felt fluent.
No bad feeling about it. So thank you. You can find rest of our episodes on YouTube. You know all of this, and also we have 2 books, one in Slovak, one in Czech. So pick your favorite language or just remember good old Czechoslovakia and buy both of them. See you next time.